Our universe operates under a strict, non-negotiable rule. Nothing, no physical object, and no information can travel faster than the speed of light. Because of this ultimate speed limit, traversing space always takes time. Even a radio signal sent from Earth to the Moon takes over a second to cross the void. But quantum mechanics introduces a glitch to this rule. It's a phenomenon called quantum entanglement, where two interacting particles become locked in a shared state, existing in a blur of multiple possibilities at once. This animation shows what happens when we pull those entangled particles far apart and measure one of them. If the particle on the left is measured and ends up pointing up, its partner on the right immediately snaps to point down. This reaction happens instantaneously. It appears to bypass the concept of physical distance entirely. Albert Einstein famously hated this concept. He refused to accept that particles could influence each other instantly across space, dismissing the idea as spooky action at a distance. Along with his colleagues Boris Podolsky and Nathan Rosen, Einstein argued that the theory of quantum mechanics must simply be missing some pieces. They proposed that these particles carry hidden variables, secret internal instructions dictating exactly how they will act before they are even measured. Think of it like this diagram of two boxes. If you pack a pair of mismatched socks, one pink, one blue, into separate boxes and ship them across the world, the moment you open your box and pull out a pink sock, you know the distant box contains the blue one. No faster than light signal traveled between the boxes. The colors were decided the moment they were packed. The question dividing physicists was whether entangled particles were acting like these predetermined socks, or if they were actually executing an instantaneous connection. Resolving this debate would determine if our reality is strictly local and bound by the speed of light, or if it allows for connections that transcend the light cone. It took decades to find the answer. In 2022, the Nobel Prize in Physics recognized the scientists who finally put Einstein's hidden variables to a rigorous physical test. Building on the theoretical framework of John Bell, physicists Elaine Aspect, John Clauser, and Anton Zeilinger built experiments to measure entangled particles through filters set at varying measurement angles. This chart shows the correlations breaching classical limits, proving hidden variables don't exist. Before measurement, particles lack fixed states, remaining a blur of probabilities until striking the filter. Entangled particles are an inseparable whole. Measuring one forces the entire unified system to collapse at once. Einstein was incorrect. The universe genuinely contains non-local connections that transcend physical space. If this single, unified system updates instantly across the entire galaxy, why can't we exploit it to send faster-than-light messages? The answer is a strict mathematical boundary called the no communication theorem, which prevents humans from breaking the rules of causality. Look at this plot of measurement outcomes. Measuring your half of an entangled particle yields a completely random result, building a perfect 50-50 split of ones and zeros. Because a sender cannot force a specific state, they cannot encode a message using pure randomness. The receiver will only see a string of random noise until both parties verify their measurement settings using a standard slower-than-light method. Relativity is safe. Entanglement is instantaneous, but transferring usable information strictly obeys the speed of light. If we cannot use entanglement to send messages, what is its actual physical value? Entanglement operates as a quantifiable physical resource, governed by its own set of structural laws. This diagram illustrates the primary rule, the monogamy of entanglement. If two quantum bits are maximally entangled with each other, they mathematically cannot be entangled with a third party. If a rogue node attempts to attach to the tether, the original link visibly breaks. The E91 cryptography protocol uses this exact monogamy rule. If an eavesdropper attempts to intercept an entangled key, the fundamental entanglement breaks, instantly revealing the intrusion. Data protection is no longer guaranteed by complex mathematical encryption, but by the laws of physics themselves. This physics-based cryptography is laying the groundwork for a secure quantum internet, connecting global hubs through shared quantum states. We are moving out of theoretical chalkboard physics. Engineers are actively building the hardware required to make these networks a reality. The very act of observation itself becomes the ultimate alarm system against data theft. The phenomenon Einstein used to question the validity of quantum theory has become the mechanism securing the networks of the next century.